go as something like mole fraction times the partial pressure times the total pressure, right? Divided by 1 plus the mole fraction times the total pressure, then this is a characteristic of a Langmuir isotherm, what they call Langmuir isotherm. And this mole fraction in statistical mechanics can be written as something like this, as some partition function times e to the negative chemical potential divided by RT. This is a, if you don't know anything about this, don't worry about it, because this you will show, if you take a statistical thermodynamics course, you will explain, people will explain how your chemical potential are related to this mole fraction. Okay, so it should, your chemical potential should relate somehow to the mole fraction, which is which reflect the interaction of absorption. Okay? So that's it. So the general term which I want people to memorize is this idea that your coverage go as something like this, right? It's essentially concentration divided by 1 plus concentration. Mole fraction times the total pressure is like the partial pressure. You know, it has characteristics that look like this term. And the characteristic picture that you see is like this. Is in fact you have coverage over the partial pressure, ties of total pressure, is go like this. In other words, we can think of this like that, which is very reasonable, I think, is that for a strongly absorbing system, whatever molecule you throw at the surface gets stuck. And so with time, your coverage should level off. The reason is that because every absorption site is being occupied, so it should plateau like this. So this is again the characteristic of a Langmuir isotherm, that when you plot the coverage with respect to partial pressure, it should go like this. It should have a form that look like this, that it approach some sort of saturation, and this saturation of course is 1 here, meaning that all the site is occupied. Okay, so those are the 2 main points that I want people to recognize, to remember the characteristic of a Langmuir isotherm. And you may see this from time to time in future, because Langmuir isotherm is very popular, and in fact it's a very commonplace absorption behavior for a lot of gases and a lot of material on surfaces. Okay, so you see already that somehow energy is involved, because you have chemical potential related to the mole fraction. So now I like to think about, in terms of kinetics, kinetics meaning that the movement of these atoms towards the surface. And usually you can think of it in qualitatively in this way. You can think of, generally as you throw a atom or molecule towards some sort of surface, because your surface, of course, also contain atoms and molecules. There will be interaction between the surface itself and the incoming particle, right, which is your atom or molecule. And usually you would have some sort of attractive term, which will hold the atom and your particle towards the surface. And of course, as you approach the surface, there will be some repulsion term. So you generally have this red curve will represent attraction, and then the blue curve represent repulsion. So you would have some sort of a potential well like this. You must have a potential well, otherwise the particle would not stick, right? Because there must be something to trap the particle in an energy sense, that when you throw the particle at the surface, it got trapped. So there must be some sort of well in there that as the particle approach, it got trapped in this well. It's below the free state, right, when it's in a free particle state, and it just gets stuck in here. Now, what are these attraction potential? There's several types that I try to show here, which is important that people recognize these type of interactions, I think, because all material have this kind of interaction. There's of course the Coulomb potential, the rather long range Coulomb potential, which are usually quite strong, because if you're talking about ionic surfaces, you have real charge on the surface, and that's very strong. And the same go with polar surfaces. If you have molecule like water, for example, is a highly polar molecule, you could have a polar electrostatic type, Coulomb type interaction, which you can polarize the molecule, and that also belong to the same type of interaction, go as 1 over R. Both of these go as 1 over R. And one is the ionic one is very strong, and the polar one, meaning the neutral, except the electron density is asymmetric with respect to non-spherical asymmetric type distribution, then you have a polar distribution of your charge, and you would get Coulomb potential as well, and that's rather weak. And of course you have covalent interaction, covalent bonding interaction, which usually occur at very short range. It goes as 1 over R to the 6th, and this is very strong. This is over 100 kcal per mole, or 25, or over 25 kilojoules per mole. And the other is a little bit weaker, and we got it for potential. And lastly, of course, the first force which usually are active in the case of Fizeau absorption that occur in very long range, go as 1 over R to the cube kind of interaction, is the van der Waals potential, right, which all material has, and of course van der Waals won the Nobel Prize because of his understanding of this long range van der Waals potential that really occur at large distance, and this is extremely weak. And typically, the energy there that you have is typically less than 5 kcal per mole. So the dividing point regarding Fizeau absorption and chemi absorption, right, is of the order of 5 kcal per mole, and we use a non-SI unit. It's about 1.5, 1.2, 1.5 type kilojoules per mole. You want to use SI unit, but in the old days, people like to think of the normal sort of historic units, which is calorie, so 5 kcal per mole. Below 5 kcal per mole, you have van der Waals interaction, Fizeau absorption state, and then above it, the other forces come in, the shorter range forces come in, like Coulombic potential and covalent potential, and that gives rise to chemi absorption. Okay, so the picture. Oftentimes, the picture you might see that in textbook that you might have is that people may make a plot like this, right? So a very similar plot, the total potential. This is in terms of R. You would have like that, right? So this corresponds to chemi absorption state, and as you go further out, there's a shallow well, and this is Fizeau absorption. Okay, Fizeau absorption. Okay, and then you have adsorption. Okay, and here you have chemi adsorption, like that. And so this corresponds to van der Waals regions, which occur at large R. Okay, 1 over R to the cube kind of interaction. As you get closer and closer, you would get chemi absorption. Once you get into, You can see why Feces absorption is rather easy to, if you have something that's feces absorbed, you can rather easy to dissolve it. It's because the well is rather shallow. This well, when we're talking about this absorption energy, this well is, of course, is less than 5 kcal per mole.